All right, great. Hi, I'm Abigail Flom, and we can go to the next slide if I understand how this works. Where do I point it? Make it. There we go. Okay, so I am going to be using a few different natural processes to try to look at how hydration on the lunar surface is affected by temperature, and I'm going to be trying to distinguish which of multiple possible processes I am looking at. So I just want to quick go over those. One way to form hydration on the lunar surface is through the solar wind ions. However, all of the observations I'm going to be talking to you about today are taken while we are in the Earth's magnetotail. So you can see that in the plot on the bottom diagram of that. And so while we are in, while the moon is in the Earth's magnetotail, it is actually cut off from the solar wind. So right off the bat, we're cutting ourselves off from that. Then we also have the ballistic migration of water molecules across the lunar surface, which Paul was talking about. And then while we're in the magnetotail, it's also hypothesized that we could get ions to form hydration from sourced from the Earth. And it's also hypothesized that high energy electrons in the plasma sheet could stimulate the production of hydration in the lunar surface. So I will be distinguishing between those last three as we continue talking. So I am using observations from the NASA Infrared Telescope Facility, IRTF telescope. I'm using the 3-micron hydration band, which is sensitive to hydroxyl and water, which I'm going to talk about together as hydration. And there's an example of that absorption band in the bottom plot. And I'm going to be exploiting the rapidly changing temperature and illumination conditions before and during partial lunar eclipses. So I'm going to be using observations from two different nights. So the May 26, 2021 is for when I talk about observations of the subsolar point. And then the November 30th, 2020 is observations of the Chang'e 5 landing site, and then the Airy Swirl, which is the main part. Okay, so why are we interested in partial eclipse? So this is a unique opportunity to observe a change in temperature that does not also have changing photometry, which can confuse the results. And we also get to watch temperature change on timescales that are much faster than diurnal timescales, which means that we can get further insight into sort of the chemistry of what's happening. And we've also previously detected the development of a 3-micron band on these timescales, and an example of that is shown in the plot above. So, so to distinguish between what mechanisms we think are like developing this 3-micron band on these rapid timescales, I am also going to use local magnetic anomalies on the lunar surface. So I'm going to be using the bright red blob in the middle of the moon on that top graph. That's the Airy swirl. So these magnetic anomalies are sometimes associated with bright albedo features, which are believed to form because the magnetic field above them protects them from charged particles. So at the swirl, charged particles from solar wind, earth wind, and plasma sheath would be deflected by the magnetic field. So we should see a reduction in the development of hydration on the swirl if those processes are involved. And then, but water molecules that are ballistically migrating should not be affected. So at the swirl, the top graph is just a reflectance image of the swirl, and I'm pointing to the swirl with the red arrow. Then the middle image is full illumination, and we're plotting the 3-micron band depth. So we can see on the swirl versus off the swirl, there is an initial difference in the 3-micron band depth at full illumination. And then the bottom image is at 60% illumination, and there we see that both of them have greater band depth, and that the initial offset has been maintained. So both of them developed a hydration band, and it's about the same amount of a hydration band formed on both on the swirl and off the swirl, which kind of gives us an indication that the deflection of charged particles doesn't affect this process, which makes us think that we're looking at the ballistic migration of water. So this is in the context then of some other observations that we've done in partial eclipse. So we've also, we observed the Chang'e 5 landing site less than 24 hours before the lander came and collected its samples and also its own spectra. So in that time frame, we went down to about 45% illumination, and you can see a map of the site as well as the surrounding area, where it climbs up to about 400 parts per million hydration over the course of a couple hours in that eclipse. And this site also gives us some comfort in the fact that our full illumination data is consistent with the results from the Chang'e 5 spectra and samples. And you can also begin to see an asymmetry between the onset and the offset of the eclipse in these spectra. That's a little better shown with the subsolar point. So this is from a different eclipse after we saw that there was something going on. We went to the hottest spot on the moon, and we just sat there and we took spectra as quickly as we could to see how this, how the band development changes with time and temperature. So what you can see with the blue data, also labeled eclipse ingress, is as the temperatures drop, a 3-micron band develops, and then there was a total eclipse, so that happened, and then we came back when there was enough light again, and we saw that the band had climbed up to an even larger portion of water, and then we watched that kind of get baked off as the temperatures climbed back again. And at the bottom, that bottom plot, you can see
1 minute left.
Okay. You can see the hydration with relation to time for the ingress. So this is really interesting because with this, we can kind of set constraints on the ballistic migration that we think we're looking at. So for example, there must be enough water present in the lunar exosphere to produce this band if it's added to the surface, and then this water must arrive at a rate that's consistent with the rate that we're seeing this observation take place, which is actually like quite rapid. So we did some back of the envelope calculations to see what this would look like. And so if you look at it like a column of water that's over one of our pixels, then this ends up coming to like 8 times 10 to the 11 molecules of water per cubic centimeter, which is way above, orders of magnitude above the LADI exospheric density limit of 1 molecule per cubic centimeter. And then we also did it looking at the rates, so how long it takes, instead of just like collapsing a column over, and we still got like 1.2 times 10 to the 9 molecules per cubic centimeter. So this could definitely use some more formal modeling, but this is like, it's really a lot of water. So it's similar to Paul's issue. It seems like we have a lot more water than we really know what to do with. So in conclusion, we see a rapid development of a 3-micron band. We see this change both on and off the Airy swirl, which seems to indicate that it doesn't have to do with charged particles. And this is consistent with observations that we've done at the Chang'e 5 site and at the subsolar point. That being said, the constraints that it places on ballistic migration are many orders of magnitude over the amount of water we think is available. So this is kind of an ongoing mystery. So thank you for your time.